of electric current. Okay, so let us start and let us focus on the objectives. What are the objectives of magnetic effects of electric current? Now I am going to share my screen. Okay, now look at the objectives. What are the objectives of the magnetic effects of electric current? Now these are the learning objectives of this topic, that is, explain the concept of magnetic field and state the properties of lines of magnetic force. Second one is infer that when electricity flows through the conductor, magnetic field is produced around it. Third one is explain the force experienced by the current carrying conductor placed in a magnetic field. Okay. And fourth point is that describe the electromagnetic induction and its importance in a different aspects of our daily life. Next one is that describe alternate current and the direct current, and the list the appliances that work on this current. So these are the objectives we have to learn in this chapter, that is effects of electric current. Okay, so now let us start the introductory part of this topic, that is means what? The force that we know all are aware about, the magnet and the magnetism. So the force of attraction or repulsion in around a magnet, it is called as magnetism. You know the process, that is a magnetism. What is means it? The attraction, that is the force of attraction or repulsion in around the magnet. Okay, so that is called as magnetism. So here look at that figure. It is the magnetite or lodestone, that is the magnetite or lodestone in an ore or iron. So this is the iron, the magnet that is found in nature. So we are already aware about the magnet. So these are the properties of magnet. So we know the magnet having two poles, that is north and south pole. Okay, so this is the north and south pole. We know the magnet, when we cut the magnet into two parts, again it behaves like a magnet having south and north pole. Okay, so again we know in 9th standard we already studied that there is attraction and repulsion between the magnet, but it having, when the south, there is a attraction between the unlike poles. Now look at that figure, south and north pole is there. There is an attraction between the south and north pole, that is the unlike pole. Okay, and next is repulsion. There is a repulsion between the like poles, that is the south pole or north. So there is a repulsion between the two like poles. Okay, now we know about the what is the magnetic field and what is the magnetic lines. So what is exactly the magnetic field? How to create it? Now look at that figure. It shows the magnet is there in the center, the cardboard. The magnet is there. The region around the magnet where its force can fade is known as the magnetic field. Region around the magnet. There is iron filings are there. Okay, look at that figure. So there is iron filings which are arranged them on the magnet. What will it shows? The region around the magnet where its force can be felt, it is known as magnetic field. Okay, so here there are the concentric circles, but these are shows in curves manner. So that is the curve in shape. So continuous curves are there. Why does the iron filings form a patterns? Why it shows the pattern? Due to the force exerted by the magnet. The iron filings arrange themselves in pattern as shown above. So due to only the force exerted by the magnet and the force mostly exerted towards the poles. It is more force is exerted by the magnet's pole, that north and south pole. Okay, so hello. So here, how is the magnetic field represented? How it is represented? So these are the, how it is the magnetic field. So magnetic field is represented by the magnetic lines. Okay, so look at the figure here. There is a two poles, north and south poles, and you can see here, there are the magnetic lines. Magnetic lines are there around which represent the magnetic field. Okay, so this is the magnetic lines. And what are the magnetic field lines? What is meant by the magnetic field lines? So what is meant by the magnetic field lines? The path along which the unit north pole, the path along which the unit north pole moves in a magnetic field. Okay, so path along which the unit north pole moves in a magnetic field, it is called as magnetic lines. And these magnetic lines of force are closed continuous curves are there. So these are the continuous curves. They start from the north pole to and ends towards the south pole. So these are the continuous lines. That is the continuous close continue curves are there. They start from the north pole and ends on the south pole. Okay, so magnetic field lines is nothing but the path. Now it is the path taken by a unit north pole when placed in a magnetic field. Okay, so it is the magnetic lines, and these magnetic lines are close continuous curves. Close continuous curves. They start from the north pole and end on south pole. So these are the magnetic lines. Again, no two magnetic lines of force can intersect to each other. So look at here, these are the characteristics, these are the properties of the magnetic lines of force. So these are the properties. Look at the diagram, there is a direction of lines, that is the direction of magnetic lines of force. So that the field lines start from north pole and it ends on south pole. Okay, so field lines start from the north pole and ends on a south pole. Second one is, there is no two lines will intersect with each other. So look at that diagram, there are the lines. So there are the magnetic lines. The two lines will never intersect with each other. Third point is there, inside the magnet, the field line moves from south to north pole. Always remember, inside the magnet, the field lines moves from south to north pole. Okay. Then fourth is what? The magnetic lines of force are crowded near the pole. Okay, so magnetic lines of forces are crowded near the pole. Here in previous slide, we can look at this diagram. In previous slide, look at this, all the magnetic lines are crowded towards the pole. Okay, not in the center. So remember that point, the magnetic lines of forces are crowded near the pole. So this is the experiment. If you bring iron filings or iron nails, so iron nails or iron filings, when you place close to the magnet, when you place on the magnet, the iron filings or the nails will get attracted
Meeting
towards the magnetic pole. Okay, so iron filings get attracted to the magnetic pole, not in the center. Okay, so because of that, the magnetic lines of forces are crowded near the poles, not in the center. So this is the experiment that shows the magnetic lines of forces are crowded near the pole. Okay, now this is the main topic, that is that will be the previous slide shows the introductory part of magnetic effect of electric current that you have already studied in 9th standard. Now we are going to start now what is the magnetic effect of electric current. So here there are the two diagrams here, there are the two figures that shows the magnetic effect of electric current. Okay, now if the electric current is made up to flow in wire, so there is a circuit. Now look at that circuit, the connect the circuit as shown in figure, right? So figure is there, the connect a copper wire. There is a copper wire here, that is the current is flowing here. For seeing this, take a conductor wire. This is the conductor wire, this is the copper wire. The figure shows the copper wire is there, there is a circuit. Now, help of the connecting wires, attach the two ends of battery. Okay, so the circuit is completed. Keep the magnetic needle parallel to the conducting copper wire. So that red color that denotes the compass, that is the magnetic needle is there, and keep that needle parallel to the conducting copper wire as shown in figure. When the circuit is complete, the magnetic needle shows the deflection. When it shows the deflection, when the current flows through the wire. When the current flows through the wire, the magnetic needle shows the deflection. Okay, and the magnetic field is produced around the current. If the current is increased, there is a greater amount of deflection. If the current is increased, the greater amount of deflection is there and the direction of flow of electric current is changed. If you reverse, if you interchange the circuit, there is a direction of flow, electric current, the direction of the flow of electric current is changed. Okay, the direction of the deflection is also changed. Okay, so it will be also changed. Now, if the current flow is stopped, the deflection in the magnetic needle also cease. Okay, so the magnetic field is an effect of flow of electric current is there. So a compass needle is a small bar magnet. The end of the compass needle points approximately towards north and south pole. Okay, the end which points towards north is called as north pole, and the end which points towards the south is called as south pole or south seeking pole. So this is the magnetic pole. Now, if in the above activity or in the figure, if we increase the current through the wire, the needle will deflect more. And if we move the compass away from the wire, the deflection of the needle will start decreasing. If we move the compass away from the wire or away from the conductor, the deflection in the needle will start decreasing. Thus, the magnitude of the field produced at a given point is directly proportional to magnitude of current. The magnetic field produced by given current in the wire decreases as the distance from the wire increases. Okay, so these are the points where when the magnet is placed near the current carrying conductor, so what will happen? So this is the experiment. It shows the magnetic field, the effect of magnetic field. Okay, so the current is stopped, the deflection of the magnetal will also stop. And if we increase the current, the greater amount of deflection is there. So this is the called as magnetic effect. When the current, that wire carries current, the wire carries electric current, it behaves like a magnet. And this process, and where it behaves like a magnet, it creates magnetic field, and all the phenomenon is called as magnetic effect of electric current or electromagnetism. So here wire, the current carrying conductor behaves like a magnet and it creates magnetic field. That's why this process, all this phenomenon is called as magnetic effect of electric current. Now look at the next slide. Here, instead of compass, instead of magnetic needle, we are going to start that there is a how it current the deflection in concentric manner when the current is passed through the straight current carrying conductor is there. So look at that diagram. Magnetic field produced around the conductor. So here magnetic field produced around the conductor. That is your next topic. What changes are caused by increasing or decreasing current? So we know that already. What do you see when the magnetic needle is kept a little away from the wire? Now instead of the magnetic needle, spread the iron filings. So here in the figure, in the experiment, take iron filings are on the cardboard and observe. The iron filings arrange themselves in a circular manner around the wire. So when the current pass through the straight current carrying conductor, when the current pass through the straight current carrying conductor, the magnetic field is produced round it. That is, concentric circles are there. These all are arranged in circular manner. Using iron filings, we can observe that they align themselves in concentric circle. So look at the figure. Second figure is there. The iron filings are arranged in concentric circles around the conductor. So the magnetic field is produced around the straight current carrying conductor if the current is unchanged. And if the magnetic field reduces as the distance from the wire increases. So the magnetic field reduces. If we increase the distance of wire, so magnetic field reduces. If we increase the distance of the wire, the magnetic field will be decreases. So here, therefore, the concentric circles representing the magnetic lines of force are shown bigger and bigger. Okay, when the distance of wire is increases. So here the diagram shows itself that the magnetic field is produced around the straight current carrying conductor if the current is unchanged. This magnetic field reduces as the distance from the wire increases. Okay, so as the distance increases, magnetic field will be decreases. Therefore, the concentric circles representing magnetic lines of force are shown bigger and rarefied as the distance from the wire increases. If the current through the wire is increased, the intensity of magnetic field is also increased. So that point is important. If the current through the wire is increases, the intensity of magnetic field is also increases. Okay, so here we can observe the magnetic field produced around the conductor where the current carrying conductor is in straight line. So that is the straight line. Wire is in straight line portion. So yeah, we know the way the straight line is there. The straight line is there. The current carried conductor is in state position. Is in state position. The magnetic lines of force shows the concentric circle. There are the concentric circles align themselves around the conductor. Okay, so this is the experiment where the iron filings are used, and we can observe the diagram. So many concentric circles are there, and these are arranged in circular manner when the position of the current carrying conductor is in straight line. Okay, so it is in straight position. Now next is what? How will you determine the direction of the magnetic field? Is it clockwise or anti-clockwise? How will you determine that the direction of the magnetic field is? So let us start the next slide. That is determines that rule determines the direction of magnetic field produced in a conductor carrying current. That rule is the Maxwell right hand thumb rule. This rule is right hand thumb rule, or it is also called as Maxwell right hand thumb rule. Okay, so look at that diagram. There is a conductor, there is a wire. Okay, and if you stretch your thumb in the direction of the conductor, it is upward direction. Your thumb is upward direction. So thumb points upward direction. The direction of the conductor is there. So look at this slide. Right hand thumb rule. Here is the conductor, the direction of the magnetic field lines, and the direction of the magnetic field lines are there. How they curve. When the current carrying conductor is held in a right hand. So when the current carrying conductor is held in a right hand and the thumb is stretched in upward direction along the direction of current. Okay, the thumb is stretched upward direction along the direction of the current. Then the fingers are curved. The fingers curve, wrap around the conductor, gives the direction of magnetic field. So that fingers which are curved, which get curved, wrap around the conductor, gives the direction of the magnetic field. So this is the Maxwell right hand thumb rule. This is also called as Maxwell's corkscrew rule. Corkscrew rule is there, or this is the right hand thumb rule. So here the direction of the magnetic field produced by the current flowing through an electric conductor. Imagine. Okay, so the conductor is in your right hand in such way that the thumb points in the direction of current. The thumb points in the direction of the current, and then turn your fingers around the conductor. The direction of the fingers is the direction of magnetic lines of force. So this is the right hand thumb rule. Now what will happen? This is the conductor is in straight position. What will happen when the conductor plays in circular manner or it is in circular loop? Let us see the next slide. That is what happens when the direction of the current flows through the conductor in reverse. So we have seen in previous slide that the right hand thumb rule, the thumb shows upward. That thumb position is in upward direction. Okay, when it is in reverse, thumb position, if you reverse the thumb position, if the thumb point is in reverse direction, what will happen? So look at the diagram. Magnetic field is there. The magnetic field shows two directions. One is anti-clockwise and another one is clockwise direction. So there are two directions here. So when a stronger current will produce the stronger magnetic field around the wire. Previous slides we have already learned that if we increases the current, the intensity of magnetic field is also increased. So when we increase the current, intensity of magnetic field also increases. So stronger the current will produce stronger magnetic field around the wire as shown in figure. Okay. So here the magnetic field strength at the center of circular coil. In previous slide, we have seen that when the current carrying conductor is in straight position, the magnetic field shows the concentric circles around it. But when the current carrying conductor these are having circular loops, what will happen? The magnetic field strength at the center of the circular coil carrying conductor. So look at that figure. It increases, the magnetic field increases when the current flowing through the coil increases. So in previous slides, we already learned when we increase the current, the magnetic field is also increases. So intensity of magnetic field increases. The magnetic field increases as the number of turns of coil increases. If we increase the number of turns of coils, the magnetic field also increases. And if you reduce or increase, if you increase the radius of coil, the magnetic field decreases. If we decreases the radius of coil, the magnetic field increases. Okay, so these are inversely proportional to each other. If the radius of coil increases, then magnetic field will be decreases. Okay, and radius of coil decreases, the magnetic field will be increases. Second point is that if the strength of the current or if the current through the wire increases, the intensity of magnetic field increases. Okay, so these are the important points. If we increase the number of turns of coil, the magnetic field also increases. Okay, if you increase the circular loops, that if you increases the coil, the turns of the coil increases the magnetic field. Okay, so next slide shows if we increases the number of loop, what is that called? If we increases the turns of that current carrying conductor, that is called as solenoid. That is called as solenoid. Now, what is meant by the solenoid? A solenoid is an insulated copper wire wounded in the form of cylinder is called as solenoid. So, this is the insulated copper wire. Okay, solenoid is nothing but the insulated copper wire. It is having number of loops. Okay, so it is looks like a spring also. It is look like a cylinder. So this is the solenoid. It is a insulated copper wire wound in the form of cylinder is called as solenoid. So the coil of many turns of insulated copper wire wrapped in a shape of cylinder. And the magnetic field lines in the solenoid through which the current is passed are shown in figure. So this is current carried conductor. It also behaves like a bar magnet. Means what? This solenoid also having two poles, that is north and south pole. So it behaves like a bar magnet. So look at the factors affecting the magnetic field strength due to the current carrying solenoid. So here, look at the figure. The number of turns, look at that figure. There is a difference, like there is a difference between the two figures. Look at the number of turns, number of loops. Okay. So magnetic field due to solenoid. Here, which are the factors affecting the magnetic field? As the number of turns of coil increases, as the number of turns increases, as the number of loops increases, the magnetic field strength also increases. Understood? Remember that as the number of turns, as the number of loops of that current carrying conductor, that is nothing but the solenoid, increases, the magnetic field strength also increases. Second point is that here, as the current flowing through the solenoid increases, the magnetic field strength also increases. Okay. Previous slides we have already learned. If we increase the current, the intensity of magnetic field also increases. So as the current flowing through a solenoid increases, the magnetic field strength also increases. Okay. Third point is, as a soft iron core. Now this is the main point. As the soft iron core is introduced, if we introduce a soft iron core inside the solenoid, the magnetic field strength also increases. Okay. If the soft core on iron, look at the figure, two diagrams are there, two figures are there. There is a difference. In first diagram, there is no bar magnet. But in second diagram, if we put up the bar magnet, that is the soft iron core is there, introduced in a solenoid, the magnetic field strength also increases. Okay. So in the diagram, in solenoid, look at the figure. These lines are similar to that of the lines of bar magnet. Now these are the lines as shown in figure here. These lines are similar to that of the lines of bar magnet. Okay. Now one end of coil acts as a south pole here in previous slide. One end of the solenoid acts as a south pole and other end acts as a north pole. Okay. The solenoid has all the properties of the bar magnet. And this solenoid, with the help of the solenoid, we can magnetize the piece of rod of given material. If the rod is hard steel and if the magnetic field is strong, the permanent magnet can be produced. Okay. If the magnetic field is strong, the permanent magnet can be produced. The permanent magnets are usually made in carbon steel, chromium steel, or it may be tungsten steel, or some alloys. So here, there is a solenoid. The properties of the magnetic field of a solenoid are very similar to the magnetic field produced by the bar magnet. One of the open end of solenoid acts as a north pole. Okay. Other end acts as a south pole. And the magnetic lines of force inside the solenoid are parallel to each other. this is the important point. The magnetic lines force inside the solenoid, the magnetic lines of force inside the solenoid, they are parallel. Okay, they are same at the point, and they are parallel to each other. What does it means? It means the intensity of magnetic field within the solenoid is uniform everywhere. Okay, so intensity of magnetic field within the solenoid, inside the solenoid, is uniform everywhere. Why? Because the magnetic lines of force inside the solenoid are parallel to each other. These are parallel to each other, so that what? These are uniform. The magnetic field is uniform everywhere. Okay. So in the solenoid, this is magnetic field is uniform everywhere. So finding the polarity of the magnetic field. Finding the polarity of the magnetic field produced by the current carrying solenoid. So here, look at the diagram, look at the figure here. If the current flows in clockwise direction, in the solenoid, there are the current carrying conductor is there. It is in the form of the turns, it is in the form of the loops. But how to find the magnetic field? What is the direction of the magnetic field if the current flows in a clockwise direction? It indicates the south pole, because the solenoid also acts as a or behaves as a bar magnet. Means what? It is also having the south pole and north pole. So one of the open end of solenoid acts as a south pole and another one is north pole. Okay. So if the current flows in clockwise direction, it indicates the south pole. And if the current flows in the anti-clockwise direction, it indicates, it denotes the north pole. Okay. So if the current flows in a clockwise direction, that denotes the south pole of the solenoid, and if the current flows in anti-clockwise direction, that is the north pole. Remember these 2 points. Clockwise, the clockwise, there is S, right? So S is the south pole, anti-AN. So there is a north pole. So remember that like that. If the current flows in clockwise direction, the solenoid, that denotes that indicates the south pole, and anti-clockwise direction, that indicates the north pole. Now here, the magnetic field due to current in a solenoid. How to produce? The magnetic field due to the current in a solenoid indicates. Now look at here. Whenever the electric current passes through the solenoid, the magnetic lines of force are produced, right? The electric current passes through the solenoid, the magnetic lines of force are produced. One of the open end of solenoid acts as the north pole and another one is south pole. Okay. And the magnetic lines inside the solenoid are parallel to each other. Okay. Inside the solenoid, the magnetic lines of force are parallel to each other. And within the solenoid, the intensity of magnetic field is uniform everywhere. That is means the magnetic field in the solenoid is uniform everywhere. And what does mean is the magnetic field due to the current in the solenoid. First point is what? When the copper wire with a resistive coating is wound in a chain of loop, that is called as solenoid. Whenever an electric current passes through the solenoid, magnetic lines of force are produced. Okay. Now this is the pattern of magnetic lines. Look at that diagram. Look at that figure. Okay. Around the south and north pole, this is magnetic line shows the curved line. But inside the line, inside the solenoid, there are the parallel lines. So magnetic lines are parallel to each other inside the solenoid. Okay. So these are the important points regarding the magnetic field due to the current in a solenoid. Okay. Now remember that the direction of the force depends on the direction of the current. Okay. And the direction of the magnetic field. The direction of the current, direction of the force totally depends on the direction of the current and the direction of magnetic field. The displacement of the rod is maximum when the direction of the current is that right angle to the direction of the magnetic field. So here there are the 4 to 5 points of the solenoid that are the important points. First is that the solenoid acts as a bar magnet. It behaves like a bar magnet. It is behave like a bar magnet. One end of the solenoid is north pole and another one is south pole. Okay. Magnetic lines inside the solenoids are parallel to each other. Okay. The properties of the magnetic field of the solenoid are very similar to the produced by bar magnet. The properties of magnetic field of the solenoid are very similar to the magnetic field produced by the bar magnet. Okay. And one of the open end of solenoid acts as a magnetic north pole and other one is south pole. This means what? If the magnetic lines are parallel to each other, this means what? The intensity of magnetic field within the solenoid is uniform everywhere. So in this lecture, we have concluded the points, summarized the points that what is the magnetic effect of electric current when the current carrying conductor is in state position. The magnetic field, magnetic lines are in the position of the concentric circles. Okay. The concentric circles represent the magnetic lines of force are shown bigger and rarefied as the distance from the wire increases. If the current is reduced, the distance from the wire increases. The magnetic field is produced around the state current carrying conductor. Okay. So there are the concentric circles represents. So there are the circular manners. All the iron filings are in circular manners when the current carrying conductor is in state position. And when the current carrying conductor is in the position of the circular loop, when it is in the position of circular loop, it represents that if we increase the number of turns, the magnetic field also increases. If we increase the number of loops, magnetic field also increases. If we increases the current, the intensity of magnetic field increases. Okay. And in the solenoid, we have learned that the magnetic field of line, there if increases when the magnetic field is parallel. The magnetic lines, the magnetic fields is lines which are parallel within the solenoid. It is uniform everywhere. Okay. So these are the points which have been covered in this lecture. That is, first is the magnetic effect, of electric current, then the right hand thumb rule and the magnetic field due to the current in a solenoid. Okay, and solenoid is behaves like a bar magnet. It behaves like a bar magnet. Both of the ends acts as a north pole and south pole. Okay, the direction of the magnetic field is clockwise. When the direction of the current is clockwise, that is south pole, and the direction of the magnetic field current is the direction of the current is anti-clockwise, that is nothing but the north pole. Okay, so